Look at a pile of scrap iron. To most people, it's just waste, a victim of time and oxygen. But to a team of engineers, this is the secret to a zero-carbon power grid. We've spent decades trying to stop iron from rusting. We paint it, plate it, and protect it. But Form Energy has done something brilliant. They've built a battery that relies on rusting to work. It's called the Iron Air Battery. It doesn't use rare minerals like cobalt or nickel. Instead, it uses the most abundant metal on Earth and the very air we breathe.
The problem with our current grid is simple. The wind doesn't always blow, and the sun eventually sets. Lithium-ion batteries are great for your phone, but they're too expensive for a city. Lithium batteries usually provide about 4 hours of backup. But what happens during a 3-day storm? That's where iron air technology changes the game, offering over 100 hours of storage. By using iron, Form Energy has slashed the cost of storage to a fraction of lithium's price. It's not about being the fastest battery, it's about being the most practical.
At the heart of this machine is a process called reversible rusting. It sounds like science fiction, but it's actually a fundamental principle of electrochemistry. When the battery discharges, it breathes in oxygen from the air. This oxygen converts the iron metal into iron oxide, literally creating rust and releasing energy in the process. To charge it back up, you apply an electric current. This forces the oxygen out, turning the rust back into pure metallic iron. The battery breathes out and is ready to go again.
This isn't just a lab experiment anymore. Form Energy has moved into full-scale manufacturing, building a massive factory in West Virginia to produce these modules by the thousands. Each battery module is about the size of a side-by-side washer-dryer set. Inside, there are 50 of these iron air cells submerged in a water-based electrolyte. These modules are then grouped into power blocks. A single block can store enough energy to power thousands of homes for days on end. The engineering challenge wasn't just the chemistry, it was the plumbing. To make this work at scale, you need a system that can manage airflow and liquid levels perfectly. If the iron gets too dry, the reaction stops. If it gets too wet, it can't breathe. The mechanical systems surrounding the iron are just as important as the iron itself. But once you solve the mechanical hurdles, you unlock a storage system that is safe, non-flammable, and entirely recyclable. It's a masterpiece of pragmatic engineering. To understand how this battery breathes, we have to look at the chemistry of the air electrode. This is where the magic and the engineering happens. Unlike a lithium battery, which carries all its reactive material inside, the iron air battery gets half of its fuel from the outside atmosphere. This is why it's so incredibly light for its size. But air isn't pure oxygen. The system has to filter out CO2 and moisture to prevent the internal chemistry from degrading. It's like a high-tech gas mask for a machine. Inside the cell, the iron isn't just a solid block. It's actually a porous pellet made of thousands of tiny iron particles pressed together. This creates a massive surface area for the reaction. Think of it like a sponge. The more holes there are, the more water it can hold. In this case, the more surface area the iron has, the more oxygen it can react with at once. This porous design is critical because iron-air reactions are naturally slow. By maximizing the contact points, engineers can pull enough current to power a grid. The electrolyte, the liquid that carries the charge, is a simple solution of potassium hydroxide. It's basically water and lye, the same stuff used to make soap. This water-based chemistry is a huge safety advantage. Lithium batteries use flammable organic solvents, which is why they can catch fire. Iron-air batteries, they're essentially full of water. Even if the battery is damaged, it won't explode. It might leak some alkaline water, but it won't start a fire. For a grid-scale installation near a city, that's a massive deal. But here's the clever mechanical part, the air-breathing electrode. It's a multi-layered sandwich of membranes that has to be both conductive and waterproof. It has to let oxygen in, but keep the liquid electrolyte from leaking out. Engineers use a material similar to Gore-Tex. It has tiny pores that are too small for water, but perfect for gas. This membrane is the most expensive part of the cell. Form Energy had to develop a way to manufacture these by the mile to keep the costs low enough for the grid. The final piece of the puzzle is the power block. This is a massive steel enclosure that houses thousands of individual cells and the systems that keep them alive. It includes pumps to circulate the electrolyte and fans to manage the air intake. It's not just a battery, it's a living, breathing chemical plant. By modularizing the design, Form Energy can build storage sites that cover acres of land, providing enough power to keep a city running through a week-long cold snap. Now, you might be wondering, if iron air is so cheap and safe, why isn't it in our cars?
The answer lies in a fundamental engineering trade-off: energy density. Iron-air batteries are heavy, really heavy. They are about 1/10 as energy dense as lithium-ion. For a car, that's a deal breaker. But for the grid, weight is irrelevant. When you're building a massive facility on a concrete slab, it doesn't matter if your battery weighs 10 tons or 100. What matters is the cost per megawatt hour.
The other trade-off is speed. Lithium-ion is like a sprinter. It can dump a massive amount of power in seconds. Iron-air is more like a marathon runner. The chemical reaction of rusting is slow. You can't use it to accelerate a Tesla from 0 to 60, but you can use it to provide a steady, reliable flow of power for 100 hours straight. This makes them the perfect partners. Lithium handles the quick spikes in demand, while iron-air handles the long-term baseload. It's a two-part solution for a complex problem. One of the most impressive things about iron-air is its thermal resilience. Most batteries hate the cold, but iron-air is remarkably stable across a wide range of temperatures. Because it's water-based and the reactions are slow, it doesn't generate the same intense heat as lithium. This means you don't need massive, energy-hungry cooling systems. This simplicity reduces the parasitic load, the energy the battery has to spend just to keep itself alive. More energy goes to the grid, and less is wasted on fans and chillers. The manufacturing of these batteries is a masterclass in supply chain engineering. Form Energy isn't mining rare earths in conflict zones. They're buying iron from the same places that make cars and skyscrapers. By tapping into the existing steel industry, they can scale up faster than almost any other battery technology. They are turning the old economy of rust and steel into the new economy of clean energy. The first full-scale projects are already breaking ground. These aren't just prototypes. They are multi-megawatt installations that will change how entire states manage their power. Next time you see a piece of rusty iron, don't just see decay. See the potential to store the sun's energy for a rainy day. See the mechanical lung that might just breathe life into our future grid. Engineering isn't always about finding the rarest, most exotic materials. Sometimes it's about taking the most common things around us, iron, water, and air, and using them in a way nobody ever thought possible. The iron-air battery is a reminder that the solutions to our biggest problems are often hiding in plain sight. All it takes is a little bit of chemistry and a lot of clever engineering.